I've already solved 10 problems, so I'll just move to problem number 11. So what we have here, we have 3 spare gears. They transmit power from a motor shaft to a machine shaft in the arrangement shown. So we have a motor here, okay, and then we have a machine here. So this is the output shaft, and the motor here is attached to the input shaft, driving shaft. This middle gear here is called idler gear. So this is the idler gear, okay? And it is supported by 2 bearings, bearing at point A and another bearing at point B. So determine the radial load on the idler shaft for given direction of motor motor rotation. So the motor rotates here in this direction, the clockwise direction. So for this direction of rotation, we want to find the reactions on these 2 bearings A and B. Okay. So determine also, so this is A, so B, determine the radial load on the bearing for the shaft rotation opposite to A. So if the shaft here or the motor here started to rotate in the counterclockwise direction, what would the reaction forces on this gear, on the idler gear would be. Right, so, and give an explanation of why these 2 answers are different, okay? First, I'm going to show you how to calculate and represent the forces on a spare gear. So if you have a pair of gears just engaged together, so there would be like forces along the line of pressure or the line of action, and then we want to understand these forces. I'm just going to try to draw here one tooth on a gear and then show the forces on them first, and then I will just write down the equations for the tangential force, the radial force, and the normal force. So first we have here, let's say we have pitch circle, right? Then we have underneath here, we have the addendum circle. And then at the top here, we have the addendum circle. Let me just get rid of this one. Nicer. Okay, so in this case, if I just try to draw here, if I connect this to the center line of the gear, then okay, so this is, if this is the center point of this gear. So what we have here, we have force, the pressure force between the 2 teeth. So we have here, this is the, we call it Wn. This is the pressure force between the 2 teeth along the line of action. Then we have 2 components. We can resolve this force into 2 components. One is in the tangential direction, we call it Wt, tangential force. One in the radial direction, if this is drawn correctly, so this will go to the center line. So this is Wr. The angle between the normal force and the horizontal line here is phi, which is the pressure angle. Okay, so if we draw here this force triangle, so we have a triangle here. So this is Wn, which is the normal force. This is Wr, which is the radial force. This is Wt, which is the tangential force. This is right triangle, and this angle is phi. So simply, we can find the relation between them. For example, we could say here Wr is equal to Wt times tan phi. Okay, so normally phi is given as a pressure angle, it's a standard value. But in order to find the radial force, we want first to find the tangential force. The tangential force, if we consider that this is a driven gear or the wheel, and it rotates in this direction, so there is a torque here, the torque that is going to the shaft of this gear. If this is the driver, so this is going to be the input torque or the input power. It just rotates also here in this case, because I assume that this is a wheel or this is the gear, so it rotates with angular velocity omega, capital omega. Okay, so Wt, the tangential force, is equal to the torque divided by R, where R here is the radius of the pitch circle of this gear. Okay. Right. So this is one way of finding the tangential force. So if the torque, the output torque, is known, so we can calculate the radius of the pitch circle, and then we can find Wt. If the power is known, so it is the power divided by the pitch line velocity v. So this is W sub t again. So the v here is the pitch line velocity, and in this case it is equal to omega multiplied by r. Okay, in meters per second. So this is how you work out the forces in a pair of spare gear, right? In our case here, they say we have two cases. Case number one, where the pinion rotates in the clockwise direction, and then case number two, if the pinion rotates in the counterclockwise direction. What would the difference be on the bearing forces? Right. So what I'm going to do now, I'm just going to try to draw the free body diagram on these three gears. So we have here the pinion, and then we have here the idler gear. And then we have here the output gear. Okay. So in this case, so the pinion rotates in the clockwise direction, and then consequently this idler gear is going to rotate in the counterclockwise direction, and this rotates in the clockwise direction. Okay, so this is case number one. So case number one. In case number two, we have more or less the same, only one difference. So we have, this is our pinion, this is our idler gear, this is our output gear. Okay, then we have the direction of rotation reversed. So this, in this case, this rotates in the counterclockwise direction, this rotates in the clockwise direction, this will rotate in the counterclockwise direction. Okay, so we want to figure out the directions of forces here, both the radial components and the tangential components, and also the resultant force on the idler gear for these two cases. Right? So what we have? So first here we have the radial components. So the radial components here, it's called separating force. It tries to separate the two gears. So it pushes the pinion upwards, and it pushes the idler downwards. So this is WR, this is WR. Okay. Then we have the tangential component. In this case, it's going to be in this direction. In this case, it's going to be in this direction. So for both Wt and Wr, we use the Newton's third law, okay? Because these two forces, Wr, are equal and opposite. Wt here are equal and opposite as well. The idea is that if we consider that this is the driver, this is the driven, so it means that in this case, the Wt is opposite to the direction of rotation of the driver. That's why Wt goes in this direction, and it goes in the same direction as the driver. So that's why it goes in this direction. Okay. Then, if we consider the, let me just big numbers. So 1, 2, 3. So if we consider 2 and 3 in this case, so 2 drives 3 actually. So in this case, I'm gonna just remove this to avoid confusion and say, okay, first I've considered 1 and 2. So here I've considered 1 and 2. And in this case here, I'm going to consider 2 and 3. So 2 and 3 here, 2 drives 3. So 2 here is the idler, and in this case it drives 3. So this is the driven, okay, gear in this case, and the idler gear is between brackets is the driver when we consider 2 and 3. Again, we have two separating forces, which is WR. Okay, they are equal and opposite based on Newton's third law. Then because the idler gear in this case, in this gear set is the driver, so the force goes in the opposite direction. So the force in this case goes in the opposite direction to, so if you just, this rotates in this direction, so WT goes in the opposite direction. For the driven, it goes in the same direction. So this is WT. Well, so how these forces are going to transmit to the shaft here, the shaft of the idler gear. Okay, so this is our next step. Another completely different color should be maybe this cyan. Okay, so this force here transmits in this direction. So this is WR. We have WR here coming from the right hand side. Then if you think about this force also as a horizontal force goes in this direction. So this is WT. Then in the vertical direction, we have this WR here. So it goes in this direction. So we have WR. Okay. And then this force here, WT, goes in this direction as well, WT. If you think about this WT and this WT, these two forces, because the idler gear is in equilibrium, so if you take the torque around the center line, so these two forces are equal because the radius is the same. So this is case number one. In case number one, you see here the horizontal forces, the two components add, along the vertical line, the two components add. Okay, this is going to be the main difference between these two. For case two, so the pinion here, or the driver in this case, rotates in the counterclockwise direction. So this is again number one, this is number two, this is number three. Okay, then in this case we have here the driver, and this is the idler. If we consider 1 and 2, so the idler here becomes the driven. Okay, then we have separating forces that goes to the center of both gears, and it is WR. So they are equal and opposite. In this case, the driver rotates in the counterclockwise direction, so the force WT here goes opposite to that, so it goes to the left, so WT. Okay, so and then here the force goes with the same direction as the gear, so it goes in this direction, so this is WT. So these are the forces on both gear number 1 and 2. If we consider 1 is the driver and 2 is the driven. When we consider 2 and 3, in this case 2 drives 3, so I'm just gonna get rid of this to avoid confusion, and I'm gonna call this the driver in this case, and this is the driven. Okay, then what we have here, our separating forces, WR, equal and opposite. And then because this is the driver, so the force WT, or tangential force, is in the opposite direction. So WT goes in this direction on the driver, goes in this direction downwards on the driven. Okay, now back to this interesting color. So what we have here, we have WR coming out, right? So So this is WR. And then we have WT coming from the left. Okay. Then we have WR coming from the top. And then we have WT coming from the bottom. So if you compare the forces on the gear, on the shaft here, on the idler shaft in both cases, you see on the right hand side, you have the two components add, on the left hand side, the two components subtract. Right. So back again here, so considering the first case where the pinion rotates in the clockwise direction, so these are the forces on the idler gear, as we have shown on the previous slide. And in order to find WT and WR, we need to make some calculations first. Remember here, the torque was given as 100 Newton meter on the pinion, and we assume here no losses, so the power transmits from the pinion to the idler to the gear without any losses. So in this case, we can calculate the WT based on the pinion, and then the same WT goes on the gear. WR is the same. All right, so for the idler gear, the diameter of the idler gear is equal to the module multiplied by the number of teeth. So if I go back here, so the number of teeth on the idler is 32. The number of teeth on the pinion is 16. The number of teeth on the gear, the output gear, is 24. 1700 RPM is the speed of the pinion and the motor. 100 Newton meter is the torque. The module is 4 and the pressure angle is 20. The pressure angle and the module are the same for all the gears, right? So the module here is 4, and we have 32 teeth on the idler, so this gives us the diameter of the idler. Also, we can do the same for the pinion. So the diameter of the pinion is the module, which is 4, multiplied by the number of teeth, which is 16. So this gives us 64 millimeter. So WT can be calculated based on the torque and the radius of the pinion. So the torque was given 100 Newton meter. So that's why here we should convert this to meters. This is the diameter, 64. We divide by 2 to get the radius. So this is 3125 Newton. Okay, so this is WT. So the force here, WT, is known now. So we need to calculate WR next. So WR, based on the equation that I've shown, WR is equal to WT tan phi. So WT is 3125 multiplied by tan phi, where phi is 20 degrees. So this gives us 1137.4 Newton. This is the radial force. So in this case, back again here, guys, you see that WR, then WT, they go in the same direction as the horizontal component. Then WR and WT, they go in the same direction as the vertical component. So if you wanted to calculate the normal force here, or the resultant force, so it is the square root of the vertical component squared plus the horizontal components squared. So in this case, we add the two, the tangential and the radial components together, and eventually we get the normal force as 6,027.9 Newton. Okay, so Wn is known now based on Pythagoras theorem. Then we have to calculate both the reactions on the two bearings of the shaft, or the idler shaft, based on the geometry of the shaft. So what we have here, we consider that we have a single force only affecting the shaft, or applied to the shaft, and then we have RA and RB, the action forces are unknown. So using the equilibrium equations here, we can calculate both the reaction forces at point A and point B. Okay, so if we take summation the moments at point B is equal to 0, so we can say Wn multiplied by 75 is equal to RA multiplied by 50. Then this gives us RA, because Wn is known, so we can calculate RA. Then we say here for Wn plus Rb is equal to Ra. This is when we consider that the forces in the y direction is equal to 0. So in this case we can calculate Rb as well. So based on the force, the normal force on the gears, we can calculate both the reactions, right? In this case, for case number 1. For case number 2, when the pinion rotates in the counterclockwise direction, you see here the two components, they subtract. So Wr is going in this direction, and then this Wt, when you just move it here, so Wt, so they subtract, and then this Wt here, and then this force here, they subtract as well. So we have Wt, Wr, okay? So these two components, they generate torque, but they cancel because it's in opposite directions. Right, so in this case, the vertical components is the difference between Wr and Wt, and the horizontal component is the difference between these two forces. That's why the normal force here, or the resultant force, is less compared to the previous case. So the ratio between the normal force in the second case, case B, and the case A is 0.47. So the ratio between them is almost 50%. So once you reverse the direction of rotation of the motion, so the forces or the reaction forces reduces by almost half, or exactly 47%. So based on this ratio, we can multiply the reaction at point A by 0.47 and the reaction at point B by 0.47, and the reaction forces values are shown here. Okay, so the next problem, actually problem number 12, we have already solved before in a previous video, so I'm not going to solve this again, save you some time. So we're going to move to problem number 13. So what we have here, for a single stage speed reducer given below, so we have here a single stage speed reducer. We have the pinion here, okay, and then we have gear. So the pinion is driven by an input shaft, and the driver or the gear or the wheel drives an output shaft, right? So it says all the information is given here. Estimate the forces on the pinion and gear shafts if the power transmitted is 0.5 horsepower. Okay, so what we have here, we have the power given. Okay, so we understand that the power is used to calculate the tangential component of the force now. So what we have also, we have the number of teeth on the pinion, 18. The RPM of the pinion is 1800. The module for both pinion and gear is 3. Pressure angle is 20. The number of teeth on the gear is 36. And the RPM of the gear is 900, right? Then we have also the geometry. The distance from here to here is 50 mil, and the distance between here to here is 50 mil as well. So we want to simply calculate the two components, the tangential component, the radial component of the force. If we assume that the pinion here rotates in the clockwise direction, so the gear or the wheel is going to rotate in the counterclockwise direction. These two circles are the pitch circles for both pinion and gear, and then here in this case, because the pinion is the driver, so Wt here is in the opposite direction, and the Wr is the separating force. It tries to separate the two gears, and then Wt on the driven gear or the wheel goes in the same direction of rotation. Okay, so the next step is to try to find and calculate both the tangential and the radial components, right? Don't forget also that we have Wn, which is the normal force, and the angle between this normal force and the tangential component is the pressure angle. We have to calculate the velocity of the pitch point. because this will allow us to calculate the tangential component of the force. In order to do that, we need to find the diameter of the pinion first. So we use this nice equation. The diameter of the pinion is equal to the module multiplied by the number of teeth. The module is 3, number of teeth on the pinion is 18, so this gives us 54 millimeter diameter of the pinion. So the pitch line velocity is omega multiplied by r, where omega here is 2 pi times n over 60. And here in this case is 1800. So and then the r here is this value divided by 2. Okay, but we have to convert this value into meter, because to have this in meters per second, right? So using the power transmitted, so we can calculate the tangential force. We have it here in horsepower. So 1 horsepower is equal to 745.7 watts. Okay, so if this is half horsepower, so this value is half of this value, and then the WT, if you remember, WT is equal to the power divided by the pitch line velocity. So the pitch line velocity is 5.1 and the power is given in watts, so this gives us the tangential force or the tangential component in Newton. Remember also that WR is equal to Wn times tan phi. So the WT is being calculated, and then tan phi, the pressure angle is 20, so this gives us the radial component as well. Based on these two components, we can calculate the normal force, which is based on the Pythagoras theorem, is the tangential component squared plus the radial component squared. So the same Wn is the same on both the pinion and the gear. So the next problem we have here, we have a gear, has a mass of 900 kilogram and a radius of gyration of 0.6 meters. So the mass of the gear is 900, the radius of gyration is 0.6 meter. It has 300 teeth, so the number of teeth here is 300, and the module is 5 millimeters, so the module is given. If owing to incorrect form, the speed fluctuates or the speed of the gear fluctuates by plus or minus 0.04% of the speed, of course. So the speed is given here is 300 RPM, and then the fluctuation of the speed is plus or minus 0.04% of this 300 RPM. Okay, so what is required here? Find the variation in the torque. So we need to find the variation in the torque. Okay, and then also the variation in the pressure, tooth pressure. The tooth pressure is Wn. This force is the pressure force between the two teeth. Okay, we're going to assume here that we have constant acceleration, deceleration. Well, so in here, based on Newton's second law, if we have an object rotates, so the summation of the torque on this object, external torque, is equal to the inertia forces. The inertia forces is the moment of inertia multiplied by the rotational acceleration, right? So if we were to apply the fluctuations, so the fluctuations happens to the speed, consequently it affects the acceleration, and as a result the torque fluctuates as well. So the plus or minus t here means the fluctuations in the torque is equal to the fluctuations in the inertia forces. Okay, so we can here calculate the moment of inertia. The moment of inertia is constant, it does not change because it is a function of the mass of the gear and the radius of gyration. So the mass is given as 900, and then the radius of gyration is 0.6 squared based on this equation. So we have 324 kilogram meter squared. Okay, so now in order to calculate the variations or the fluctuations in the torque, we need to calculate the fluctuations in the angular acceleration alpha, plus or minus alpha. Okay, so the plus or minus alpha is equal to fluctuations in the omega divided by the time, which is the time of contact. Okay, so first, what is the fluctuations in the speed or the angular velocity? It is 0.04% of the given velocity. So 2 pi times n, which is 300 divided by 60. This gives us the speed, and then multiply this by 0.04 pi divided by 100. So this gives us 0.004 multiplied by pi, which is radian per second. Okay, so this is the fluctuation in the speed. In order to calculate the time of contact, this is a rotational motion. So the time here is equal to the theta divided by omega. Okay. So if we consider that the time of contact for one pair of teeth only, so theta here, or delta theta for this particular tooth, is equal to, so delta theta here is equal to 2 pi divided by 300, which is the number of teeth on the gear. All right, and omega is given 2 pi. The omega here is given as 2 pi times 300 divided by 60. So based on these two, we can calculate the time of contact as well. If you substitute the time of contact and the variation in the speed, so this gives us the variation in the angular acceleration, which is going to be 6 pi. So as a result, the fluctuation in the torque is equal to the moment of inertia multiplied by the fluctuations in the acceleration. So the moment of inertia is 3 to 4. The fluctuation in the acceleration is 6 pi. This gives us fluctuations in the torque as plus or minus 6,110 Newton meter. In order to calculate the fluctuations in the pressure, we've assumed here that we have only one tooth in contact, okay, at any time, at any point in time. So this is the worst case scenario, actually. In this case, the load, the total load is carried only by one pair of teeth. Okay. So in order to calculate the fluctuations in the force, we have the torque. We have the fluctuation in the torque plus or minus T. Now this is known to us. It's 6,110 Newton meter. Okay. So based on that, we can calculate the fluctuations in the tangential component, of course, and then consequently we can find the fluctuations in the radial component and the normal component. In order to find that, we need to calculate the radius of the gear. So the module is given as 5 and the number of teeth is given as 300. This is divided by 2 because actually D is equal to M times T. If you were to calculate R, so it's MT divided by 2. Okay, so this is 750. So the fluctuations here in the tangential component is plus or minus the torque divided by R, and this gives us this value here. Okay, so this is the fluctuations in the tangential component, and then WT, focus that this is T, so WTR is equal to WT by tan phi, and also delta WN is equal to root delta WT squared plus delta WR squared. Okay, right. So next and last problem. So what we have here, we have a pinion with a 25 teeth. So the number of teeth on the pinion is 25. Is cut with a tool of 2.5 millimeter module. So the module of the pinion and the tool that cuts the pinion is 2.5 mil. And the pressure angle is 14.5. So this pressure angle is for the pinion and for the tool that cuts the pinion. Okay. It is made to mesh with a rack. This rack is the straight gear, if you want. Something similar to that. Okay, so this is the rack. And the idea behind the pinion and the rack is to convert the rotational motion into linear motion and vice versa. Okay, so it says here it is made to mesh with a rack having a straight sided teeth at an angle of 70 degrees. So this is the with the pitch line. So this is the angle here between this is the pitch line. The pitch line is here. So the angle, just change color. So the angle here is 70. So the angle between these two lines is 70 degrees. Consequently, if you draw a vertical line here, so the angle here becomes 20. Okay. So this angle here, 70. Again, this angle is 20. Okay. Right. So this is important actually, because eventually this 20 is going to be our pressure angle during the contact of these two gears together. The pinion rotates at 120 revolution per minute. Determine the speed of the rack. So the speed of the rack is equal to the V, or the pitch line velocity of the pinion. Okay, so this is our assumption now, that the speed of the rack is equal to the pitch line velocity of the pinion, assuming that the contact occurs on the involute portion of the pinion, right? So the velocity, the pitch line velocity, is equal to the rotational velocity multiplied by the pitch circle radius of the pinion, right? So in order to find V, we have to find omega and R. So the R is the pitch line velocity, the pitch line radius of the pinion. So R here is equal to the module multiplied by the number of teeth divided by 2. So the module here is given as 2.5, and the number of teeth is given as 25. Right. So we have here 2.5 multiplied by 25 divided by 2. This gives us the pitch center diameter, the pitch circle radius of the pinion, right? Then we're going to calculate another radius, which is the base circle radius. So the base circle radius, there is a relation between the base circle radius and the pitch circle radius, as we've seen before. So RP, the base circle radius, is equal to the pitch circle radius multiplied by cosine phi. Okay, so in this case it's going to be 30.25. The base circle radius does not change regardless of any errors or any changes in the center distance. So if there are any change happens, so the location of contact point can change, but the base circle, this is where, if you remember, if this is the tooth, so we said at some point here, this is the base circle, where this portion here of the tooth is the involute part. So the radius of this base circle does not change. So this value is the same. It's constant regardless of the conditions of the contact, right? Why I'm saying that? Because here, as soon as the pinion, which is here, you see, okay, and the rack, let me just use a different color. So the rack here, as soon as these two come in contact, so based on the geometry here, as I said earlier, this angle is 70 and this angle is 20. So you'll find out that the angle here, the pressure angle here in this case, is going to be 20 based on the geometry. Okay, so when they are meshed together, so the pressure angle is 20, and this changes the pitch circle radius of the pinion. Okay, because it is based on how they mesh together. Okay, R, which is the pitch circle radius, is equal to the base circle, which is the base circle radius, which is constant, divided by cosine phi. So in this case, because of the configuration or the arrangement here, the pressure angle has changed. It is 20, and consequently the value of the pitch circle radius changes. The base circle radius is the same as before. It does not change because this is where the involute part starts. Okay, so the base circle radius is 30.25. The new pressure angle, it is new in the sense that it is based on the arrangement here. It is 20, but the 14.5 pressure angle, the one that was given here in the problem, it is based on the pinion itself. So we have a pinion, it is being cut. The pinion, it is being cut by a tool that gives us this pressure angle and this module. Okay, but here, based on the arrangement, so the contact points between the rack and the pinion, they change. Consequently, they change the location of the pitch circle radius. I said earlier, the pitch circle radius is an imaginary circle, so its location can change, but the base circle does not change its location, because this is kind of a physical position where the involute portion of the tooth starts. Based on this arrangement, we have found a new value for the pitch circle radius, and consequently the velocity, or the linear velocity of the rack, is equal to omega multiplied by r. Omega here is equal to 2 pi n over 60. So the RPM of the pinion is 120, and then the radius, or the pitch circle radius of the pinion in this configuration, is 32.2 based on this equation here. So the velocity, the linear velocity of the rack is 404.05 millimeter per second. So in this case, you remember that the base circle radius does not change, and the pitch circle radius can change based on the configuration.